while the first part of this exercise was a bit complicated, I can tell you that this last part 2 is quite straightforward. All we're going to do is just come with a counterexample to show. Okay, so what we're asked to show is that the requirements of the legality of the substitution is necessary in the rule. So given an example of a gamma and a formula A where gamma satisfies A, where the substitution T for X is illegal, and a structure M which satisfies gamma, which satisfies A but not A with the substitution. So if M satisfies, so we want to find M which satisfies A but not A with substitution, and if it satisfies A, then it's true for every valuation, okay? And if it doesn't satisfy A with the illegal substitution, then it's not satisfied, then it's not valuated to 1 under every evaluation. So think about that for a second. What structure M can we create which under every single valuation evaluates A to be 1, so true, but there are valuations in this structure where the illegal substitution makes this false. Okay, I'm going to pause here for a second because you might be able to think of a structure by yourself. I can hint that M is the same as we've used previously. Okay, so M, same as last time, is just the set with the numbers 5 and 6. And here we're going to let P be a binary relation under M. So P is just going to be defined as the pairs 5 and 6 and 6 and 5. And then we're going to let A be equal to existence T in P with X and T. So we are going to show that under this M here and this P here, that M satisfies this, but it does not satisfy this with the illegal substitution. Okay, so first, for this to be satisfied under any assignment V, so this is equal to 1, if and only if there is an X in M such that, so we have existence, so if there is an X in M such that this, where we map T to, on the valuation where we map T to A, is equal to 1. So this again is true if and only if we have this X under M and V and this T under M and V as an element in P under M. And this again is true if and only if we have an X under this valuation, a pair with an X under this valuation and an A under this, and an A in M in P. So essentially what they're saying is that we need to have, there must be some A for every single valuation that we can evaluate X to. So what type of assignments can we have? Well, we can only assign X to either be 5 or 6. So if we assign X to be 5, then we're looking for some other A in M which can go into the pair, and we can just choose A equals 6 because 5, 6 is an element in P. And if we let X to be mapped to 6, we can just set A to be 5 because we have the pair 6 and 5 in P. So this holds. For every single valuation, this is set to 1, hence M satisfies existence T with P of X and T. Okay, so now let's look at the illegal substitution. So the illegal substitution, so this substitution is illegal because we cannot substitute T for X in A because, look here, in A, T is not a free variable. So we can't make the substitution. But we're going to do it anyway, so we're going to do an illegal substitution, which gives us ET, P, TT, and we will then see that M does not satisfy this. So for this to be true, so for this to be evaluated to 1, we need to find an A in M such that PTT equals 1, where we map T to A, which means that T under MV, a pair with T under MV and T under MV must be in P, which means that there is an A in M such that there is a pair with A and A in P under M. So if you look up at what P under M was just 5 and 6 and 6 and 5. Hence there is no A in M for which we have a pair with both. So for this to be true, we would need to have like a pair with 5 and 5 or 6 and 6. But we don't have those. So So yeah, this is not hold. In fact, it doesn't hold under a single valuation under this M. Hence, M does not satisfy this illegal substitution. Hence, we cannot conclude that the rule without this requirement for legal substitution is sound.